Alright, now we will get into the one situation that is significantly different than anything we saw when we dealt with monoprotic species. How do we calculate the pH and concentration of other species if we start with the intermediate form, which can go either way, making things more complicated? It could lose a proton or it could gain a proton. Well, the bad news is if you tried to use ice tables to figure out how this works and this works at the same time, meanwhile H plus and OH minus have their own equilibrium in water, you go down a rabbit hole and the problem is extremely difficult. The good news is, turns out there's a very simple formula for calculating the pH, and it's this. The pH is equal to 1/2 of pK1 plus pK2. The condition is the intermediate concentration must be significantly larger than K1, which it always will be in this class. So, for the initial concentration of the diprotic acid in its intermediate form, use this formula for the pH, and we'll prove momentarily that the concentration of the basic form produced actually winds up being equal to the concentration of the acidic form produced. So you can really solve for either one of them, and then you've learned the other. And typically, it's easier to use this acid equilibrium here and solve for the concentration of L-, and then that's just going to be equal to this concentration here. Again, we'll prove that momentarily. For now, you should honestly write down everything on this slide since it's very new compared to anything we've seen so far. So pause the video and write. Now, since this is a new concept, I will do a sample problem by hand, but first let's just address where this pH formula came from. It's a rather extensive derivation, but it links a bunch of ideas together. So first we start with...
What?
It's just a derivation. Relax. Anyways, what we do next is... But it's a really nice derivation.
Yeah, you should just stop.
Fine! Okay, you don't have to know it, but I'll still leave it in the slides just in case you're interested. Anywho, let's do a sample problem. So, for, let's say 2.00 moles per liter initially, of HL intermediate. We start with that, we put it in water. What happens? Well, we will get a pH equal to 1/2 of pK1 plus pK2, which we can find from earlier in these slides where I presented both K values and then we just negative log for the pKa's. And we would get 2.328 plus 9.744 close parentheses, equals 6.036. Done. There's our pH. And so with that information, we can learn what concentration of H plus we have. We can also figure out how much hydroxide we have. But what if we wanted to know about L- and H2L+? Well, as I said before, as long as we find one, we find the other. And the easier one to solve for is the basic form from EQA2. And the reason it's easier is because we're typically given the Ka values up front, whereas we have to solve for the Kb values. So let's do it. For concentration L-, use EQA2. And I'll write it out. HL dissociates into a proton and the fully deprotonated basic form, L-. And then let's write part of our ice table, specifically the end, at equilibrium. Here's what we have. We know that HL will be 2.00, our initial concentration minus some change. And I'm going to skip over to the L- and say that this will have gone up by some amount x. But this is where things get a little weird, because we already can figure out what the equilibrium concentration of protons are, because we already figured out the equilibrium pH. Remember, when we calculate pH, we're calculating the pH of the solution after everything is done. And you might think that this number should equal that number, but it doesn't. As for why that is, well, it's not intuitive at all, but it just has to do with the complicated equilibria that are occurring in this solution. If you're interested, I'm happy to talk about it in office hours, but we don't need to understand it for the purposes of this class. We just accept it. And so, we just calculate that H plus concentration by doing what we always do with a pH value, 10 to the minus pH. Solve that properly, and we will get 9.20 times 10 to the minus 7. And that is equal to the H plus concentration at equilibrium. So we're going to plug that number in over here, 9.20 times 10 to the minus 7. So our equilibrium expression looks like this. K2, and just the second one because we are using that second acid dissociation equilibrium, is equal to 1.80 times 10 to the minus 10, which I just got from over here, is equal to 9.20 times 10 to the minus 7 times x over 2.00 minus x. And then I can still small x like I have in the past. Small x. But only this part in the denominator. That's the only plus or minus x term we see. And if we do it right, we will get x is equal to 3.91 times 10 to the minus 4. 3.91 times 10 to the minus 4, and that is, of course, molar. And then that winds up equaling our L minus concentration. And now I'll cram one more note into the bottom right corner for the concentration of H2L plus. Well, that's just equal to the concentration of L minus, which we just solved for, so we're done. If you're interested in seeing the proof for that, just go to slide 15. So let's put in parentheses slide 15 for proof. And I will show you that. It'll just all be on the slide since there's nothing really new to see. Are we sure that we don't want to do this? Okay, fine. So what if we wanted to find the H2L plus concentration using all of the math? Well, we would start by writing out that second base equilibrium, where HL takes a second proton to form the fully protonated acidic form. It also leaves behind hydroxide, and we can calculate the equilibrium concentration of hydroxide from the equilibrium concentration of protons that we get from the pH that we started with in this problem. And then a similar situation will emerge. We set up the K expression, we find Kb2 from the prior slides, we plug these numbers in appropriately into the other side of the equation, we do a small x and solve, and we get the exact same number that we got for the L minus concentration on the prior slide. And so we really do only have to solve for one of them. And so to summarize all of the various calculations that you've been learning, go to slide 16. It gives you details on calculating concentrations of various species and the pH values for initial amounts of acidic, intermediate, or basic forms of our species. Okay, that was some good groundwork for diprotic systems. That also represents the end of exam 1 material, although I'm still going to relate things we learned from here on out to what we've learned before, and kind of turn it into an exam 1 review while learning things that will technically only be on exam 2.